Thank you very much for this invitation. It's first time I am here at the Cyprus Institute, even if I'm 15 years now, I returned from the US to Cyprus. So it's first time I come here and I'm very amazed. It looks very nice. So I will start the talk. So please feel free to interrupt me if I'm running out of time, because maybe I have several things to show, and maybe I'll run out of time. But I'll start with giving basically the intuitions and the main ideas about what geometry is, and then I will proceed to applications. So there are maybe many notions of network geometry. The more classical one is that if we have a network or a graph, we can define distances as short as path distances on the graph between two nodes, right? But this is not actually geometry, just some distance metric. What I'm going to be discussing today is about a geometry that is hidden beneath real networks. And what I mean by this is that we can map network nodes into points, right, into an underlying space. These points have coordinates, and these coordinates have a meaning. I will explain the meaning. And this space is geometric. And we will see now why this geometric space is not any geometric space, but it is a hyperbolic space. It's not a flat space like a Euclidean space that maybe we are more familiar. Okay. So let me start first with some of the initial motivation. The initial motivation came from computer networks. So I had a postdoc at the Center of Applied Internet Data Analysis back in 2007, and the main problem they were trying to solve there is the scalability of routing in the internet. And there was a paper by researchers at Keita that they were saying that the number of routing control messages that have to be exchanged when there is a change in a topology in a computer network cannot scale better than linearly with the network size. And this is a big number. And even worse, in the internet, the interdomain protocol is BGP and has some certain problems that have to do with how fast routing tables converge after some change in the network. And to keep the long story short, there are a lot of messages exchanged to find new routing tables and new paths in the internet. And the idea there was, can we avoid sending updates or sending routing control messages at all? And then there was another paper there that from the computer science theory community by Robert Kleinberg that was proving that every connected finite graph has a greedy embedding in the hyperbolic plane. Means that if we have a graph, any type of graph, we can position the nodes into the hyperbolic plane such that greedy routing, I will explain now what this is always successful, meaning we can find with 100% destinations in this embedding. So in greedy routing, we assume we have packages. And if we want to send a package from a source node to a destination node, we just see the coordinates of our neighbors, the nodes that are directly connected to us. We know the coordinates of the destination that are written inside the packet. We compute distances and we pass the packet to the node that is closest to the destination in this space. And the question here is, can we always succeed in finding the destination, right? And we can succeed if the graph is in some way congruent with the underlying embedding. And here there was a combinatorial approach that you can position nodes into the hyperbolic plane such that this process works with 100% success probability. So if we want to imagine like a real world scenario, is like we are driving and we don't have a map of where we want to go. We only know distances. And then we stop at an intersection, which is a node. And based on the distances to the destination, we select to go left or right. This is not guaranteed or continue straight. This is not guaranteed to work because we may make a right, but then we may end up a dead end. At another intersection where we cannot make progress, better progress towards the destination, to reach the destination. So we can reach a local minimum. And then there we are stuck and we don't know what to do. Okay. But if the road network is congruent with the geometry, then this is not expected to happen. We expect to find roads that will lead us to the destination. So it's the same idea here. The problem with this, however, is that this embedding was enforced. It was a combinatorial approach that was enforcing the graph to be embedded into the network. And if you had a change in the topology, like a link or a node fails, then you have to recompute everything from scratch. Then at the same time, there was another paper from the physics community now that was indicating that beneath the topologies of real-world networks, there are some hidden metric spaces. And the main reason for these findings here is that real networks have strong clustering. Strong clustering means triangular subgraphs. So if node A is connected to node B and node A is also connected to another node C, then B and C have high chances of also being connected, right, forming a triangle. And in the metric space, the most basic property of a metric space is a triangle inequality in an underlying metric space. So the conjecture here was that since we see many triangles in real-world graphs, there is some underlying hidden space that is formed by node similarities that is enforcing these triangles because of the triangle inequality, and we see many triangles in a graph. So combining these two studies, we have this question, what is the hidden geometry of the internet? Because we are wanting to find what is the natural geometry of the internet graph at the autonomous system level, how ISPs are connected, and whether we could use this geometry actually to do what Kleinberg was showing that can be done in a combinatorial and enforced kind of matter in this study here. So the bottom line is that we have a network, is the graph that you see on the top, and we assume that nodes in the graph have mappings into an underlying geometric space. They have coordinates, and we want to find what is the hidden or natural space in the internet. This was the original idea, and whether we can use this space now to facilitate this greedy routing process, to find destinations in this network. So this is the problem. So the questions I'm going to address today is why geometry, what kind of geometry, what do the node coordinates represent, how we can infer the node coordinates in real networks, because we want to facilitate real-world applications, we need to be able to infer the coordinates in real networks, and what we can do with the coordinates. Okay. Why geometry? I already more or less answered this question. So real networks are characterized by two universal properties. The first property is strong clustering. This means that if node A is connected with node B and node A is connected also with node C, there is a high chance to see link between B and C. And this clustering implies geometry. There is some kind of underlying space formed, imagined by similarity attributes of nodes. There is some triangle inequality, and this triangle inequality is enforcing these triangles on the graph, on what we observe graph. However, at the same time, real-world networks are heterogeneous systems. So we have nodes that have higher degrees than other nodes. We have hubs, for instance, in the air transportation network. For instance, Heathrow is a hub in the network of how flights are connected. But we have hubs in the internet too. We have big ISPs, and we have hubs everywhere. So nodes are heterogeneous. They are not the same. And the degree distribution in these networks, in real-world networks, can often be approximated by power laws, meaning it's pretty skewed. So we see the distribution looking something like this. So there are some few degree nodes that have very high degrees, a few nodes that have very high degrees, and we don't see this, which is a Poissonian degree distribution. This heterogeneity now implies that the geometry is not Euclidean, and I will explain why. If we have hierarchies, something is hierarchical or tree-like, then this tree-like hierarchy can be approximated by hyperbolic space. But also, hyperbolic space captures not only hierarchical representations. In the limit of some limit, I will explain what limit. This hierarchy can be very, deep, can be more shallow, and can be no hierarchy. So you can also get this picture here. So it encompasses everything. Okay. This now is a known like a famous picture from this paper here. This was like the first big paper we ran on these topics here, and explains the main intuition behind hyperbolic geometry. So if we are nodes, we can see. So here in this picture, suppose these circles represent nodes, okay, in a network, and these nodes are set. The circles are set. that consists of the attributes of the nodes. For instance, if I am a node in a social network, I have some interests, right? I like, I don't know, mathematics and football, let's say. So I have a set here, right? I may be a node in a brain network. I'm a region, I'm a voxel in a brain, and I perform some specific, I'm activated under some specific activations or perform specific tasks. Okay, some attributes, abstract attributes. The intersection between sets show how similar the nodes are. So the larger the intersection, the more similar two nodes are, right? And the more likely they are connected in the observed network. The sets, however, they are not all the sets the same. You have some sets that are bigger than the other sets. For instance, you have this set here that corresponds to a node that overlaps with all other sets. Okay. This intersection of sets, which are heterogeneous sets, can give rise to this hierarchy from a Euclidean space R2 to hyperbolic space H3. So how this mapping is done, the center of each node here is this point here on the hierarchy, and the height on the hierarchy is equal to the diameter of how big this set is, basically. So this bigger set is top on the hierarchy, and like this you can build a tree-like hierarchy. This is not exactly a tree, it's approximately a tree because there are intersections between sets. Okay, not all sets are contained with each other, and these intersections are shown here by the dashed lines. So the idea is that if I want to compute distances between nodes in a network, the distances are not Euclidean. For instance, the distance from this node to this node here is not just a straight line, but I have to navigate this hidden hierarchy to find the real distance to the node I'm interested in. So the distance from this node here to this node here is that I have to zoom out on the hierarchy, go to the, say, this common ancestor, and then start zooming in. So we do a zoom out, zoom in, which is exactly what Google Maps is doing, exactly what we are doing in the same idea. If we want to fly from here, say, to US, we zoom out, we go to some central hub, say in Europe, and then we start zooming in to reach our destination in the US. So there is this kind of zoom out, zoom in thing that determines the distances. So the distance between here and here is this. And distances in hyperbolic space now are curves. And the hyperbolic distance in this space here, if I want to reach from this node to this node here, if I plug in the coordinates of the nodes and the formulas, is a line that bends and goes like this. So this is the real distance, and this is the real line. Okay. And this back then made perfect sense because Kate, I used to still doing some pictures of the internet like this. This is now not hyperbolic embedding, but it's the internet at the autonomous system level. Nodes here have coordinates, longitude and latitude. And if we want to think about routing, if we want to go, say, from this node here to this node there, we are kind of zooming out, going through the core of this topology here, and then zooming in again to reach the destination. So we see this kind of bending and this kind of pattern already from this topology here, which is not a bending in the hyperbolic space. Okay, so the navigation is curved, so distances are curved. So what is hyperbolic geometry? Some very simple things. We need to know only two things to understand why this makes sense. So there are many things like, okay, we have three types of spaces, Euclidean, spherical, hyperbolic, and here the geometry we're saying is hyperbolic. What we are really interested in is about these formulas here, how circle lengths and disk areas grow. It's like if we have a disk and we are at the center, and if we want to find the area after some distance from the center R, forget about this zeta for now, it's not important. It's given by this formula here. And this is proportional to e to the R. So areas and lengths grow exponentially as we move away from a point in hyperbolic geometry. And if we think now about say, in discrete mathematics, we have a binary tree, and we start counting nodes from the root of the tree. So we have one node, then two nodes, then four nodes, then 8 nodes, and so on. After a point, you want to calculate the nodes. The number of nodes is of the order of b to the r, which also grows exponentially from the root of the tree, which is a discrete structure. And so the disk areas also grow exponentially. Okay. Now, once we have this kind of abstract, say, intuition, by the way, this kind of intersections with sets, We found this mapping completely a bit even random. We are studying very much a book by Mikhail Gromov about Riemannian spaces. And this was some kind of a footnote, if I remember correctly, or some small paragraphs in some page that were saying that if you have this kind of intersections of sets, you can rigorously put them up into hyperbolic space if sets are heterogeneous. Okay, once we have this intuition, so okay, let's make a simple model of random graphs. Let's throw graphs uniformly on a hyperbolic plane, which means that, on a hyperbolic plane, which means that we assign to each node an angular coordinate uniformly at random from 0 to 2 pi, and a radial coordinate that grows exponentially with a density that grows exponentially from the disk center. And what you see here is a uniform distribution of nodes. If, according to the hyperbolic metric, it looks non-uniform to us, but according to the hyperbolic metric is uniform. And then we say, okay, let's connect each two nodes with the simplest possible connection probability function. If the hyperbolic distance, which is given by this formula there, which is the law of hyperbolic cosines, like the law of cosines, but in hyperbolic space, then we connect the pair of nodes. If this distance is less than a threshold r, where r is the radius of this disk. So for instance, the distance from this node here to the node up there is not a straight line or a line on the spherical distance, but is this line there. Okay, this blue line, it bends and it goes towards the center of the disk. In contrast, this would have been the Euclidean distance. This construction here now is very popular today. It's called random hyperbolic graphs. It even has Wikipedia pages. And since then, there is lots of work done in these models, especially lots of work by mathematicians and theoretical computer scientists, so trying to rigorously prove different kinds of properties in these models. And it turns out that this very simple model can simultaneously reproduce many properties that we see in real networks. So we can tune the distribution of the nodes in this space. We can fix the average degree. Say we want the nodes to have average degree 6. We want to build a graph, say, with 50,000 nodes. And this is more or less what we fix. Okay. We also fix another parameter is called temperature. It's related to how much strong the clustering we want to be in the network. Okay, and it turns out that this kind of simple, this very simple construction simultaneously produce many properties that we see in real world networks, like degree distribution, for example, in the internet here, assortativity, degree dependent clustering coefficient. So these properties are reproduced without us enforcing them. We just construct a random graph according to this model that has relatively very few parameters, and simultaneously we get many things that we see in real networks. Which suggests that this model actually back then suggests that this was a very good model. We are very excited to see that we could get all these things without enforcing them. And not only in the internet, in many other networks, biological networks, social networks, almost everywhere. Okay. Let's go now back to the greedy routing process to see how it works here. Actually, greedy routing in this kind of graphs is extremely efficient. Based on parameters, it can even achieve 100% success rates, following almost shortest path in the network without us having to perform any Dijkstra-like algorithms to find the path. So it finds the path by itself and remains efficient even after disturbances in the network. So if we remove nodes or we remove random links, this process that I will describe now can find bypasses. Okay, so if I wanted to perform greedy routing and I wanted to go from this node there as a source to the destination there, as a first step, I have to see which of my neighbors, meaning the nodes that are connected to me in this space, are closest to the destination. According to this hyperbolic distance formula that I showed earlier, the neighbors of this node are all the nodes that are within this weird shape region here. So in this example, it has only one neighbor, so it passes this one there, so it passes the packet to that node there. Now, as we move closer to the center of the disk, this connectivity perimeter of each node grows now, right? So this node here now has two candidates, the nodes this node here or the node up that he can pass the packets to reach destination. So he makes the calculations, distance calculations, and it turns out actually that bit more, not intuitively, but we are in hyperbolic space, that the node closer to that node there is actually this node here. So if we continue this process, we can reach a destination in very few steps. Okay. And we can see actually this zoom out, zoom in pattern that I described earlier. Okay, so this basically this picture here with this zoom in, zoom out. It's like watching this picture from the top. And we see this zoom out and zooming in taking place. Okay. And this greedy routing process, the success of this greedy routing process is also a measure to quantify how congruent the actual network is with the underlying space, right? And congruent, I mean how close the paths are. These are the paths in the graph, the yellow, with the underlying geodesics in this space. Okay. Now, what do the node coordinates actually represent? Initially, we thought that the node coordinates are some kind of similarity coordinates, right? Based on these coordinates, where similarity coordinates in hyperbolic space, we see connections in the observed network. But actually, we're a bit wrong, and we understood what the coordinates represent when we extended this model into a growing case. So real networks, you know, they're not static graphs, they grow over time. And then there was this popular theory some years ago of preferential attachment by Barabasi and Albert that say the rich get richer. This holds not only networks, maybe everywhere. And preferential attachments were saying that if I'm a high degree node in a network, then I'm popular and I have high chances of attracting more connections in the future compared to some other degree which is not so popular, some other node which is not so popular, has a smaller degree, which makes sense. And there was a specific formula there that was saying that preferential attachment is exactly linear, meaning that the probability to attract a connection is proportional to my degree, not to the degree to some power, right? If it was to the degree to some power, you're not getting this power loss that we observe in real networks. And we're trying to see what is the connection with preferential attachment, basically. So to see this, we have to go to the growing case of growing hyperbolic graphs. And once we went there, then we understood what the coordinates mean, actually. So, here I'll show how this hyperbolic geometry can emerge from very simple first principles without any abstract intuition or intersections of sets, by optimizing a product that we call popularity and similarity product of how connections are taking place. So the intuition here, if I am, say, a new web page in the internet, I may have links to other web pages that are not only similar to me, but also popular, right? Or vice versa, not only popular, I'm a link, I'm a web page, I don't have a link, say, only to Google, but I have a link also to some other page that talks about Tartini, the composer, or free solo climbing, because this is my interest. I'm interested too, and this is called homophily in the social sciences. Okay, so this is the intuition behind this model. And the mechanism in this very simple version of this model is the following. Suppose we have nodes T that are introduced one by one. So the measure of popularity here is the node birth time. So if I'm the first node that I appear in a network, my popularity is 1. If I'm the second node, my popularity is 2, and so on. And the measure of similarity here is that upon its birth, a node gets positioned at a random position theta in a similarity space. Okay. And this similarity space is a circle, okay, and theta is a random variable on this circle, basically. Okay. So this, why we use this as a measure of popularity, means all other things equal. If I appear earlier in the network, I'll have higher degree in the future, so I'll be considered more popular. But this is the simplest possible version of the model. And the measure of similarity between two nodes is just the difference of their angles. Okay. So the new connections now, if I'm a new node, if I'm a new node T, okay, in this model, I connect to M existing nodes, S, that appeared before me, such that I minimize this product. Basically, I minimize my angular distance to these nodes. I find the nodes that have the smallest product of S. S is the popularity of node S, and theta st, which is the similarity to me. So I eventually try to balance the nodes that are more similar to me and the nodes that are popular. And because I have two different metrics, I multiply these metrics to create a single metric. This is what we do if we have metrics that are of different natures, similarity and popularity. We cannot add them, we multiply them, and we create a single metric, and we connect to nodes that are minimized in this metric, M nodes, let's say. Okay. In other words, by maximizing the product between the popularity and similarity of nodes that were connected. Okay, let's say a very simple example. I'm node 1. I get position in a random position on the similarity circle. This is node 2, gets positioned there. Let's assume in this case that M is just 1, so we connect to one existing node. In this case, 2 does not have any option, so just connects to node 1. Now a node 3 comes. The similarity between 3 and 2 is pi over 3. The similarity between 3 and 1 is 5 pi over 6. And if we do this calculation there, we can see that node 2 wins, right? Because this product you see on the left is smaller than the product you see on the right. So we get this connection here. Now, if node 3 was a bit more similar to node A, even if it is still more similar to node 2 than to node 1 is still similar to node 2 compared to 1. This product here now changes direction. So the 1 times theta 1 3 is less than 2 times theta 2 3. So it prefers to connect to node 1. Okay. Now let's make a simple transformation. So here we have time and angles. Instead of time, let's map the time of appearance of nodes to a radial coordinates by taking the logarithm. So let's say that RT of nodes that appear at time t is equal to the logarithm of the time it appears. So node 1, because it appeared at time 1, logarithm of 1 is 0, so gets position in the circle. This is a length of 2, this is a length of 3. Okay, so we get rid of time and we have completely geometric description. And let's see now what is happening. We said in this model that node T connects to M existing nodes S that minimize this product, which is equivalent by minimizing this product, I just divided by 2, which is equivalent by minimizing the logarithm of this product, because the logarithm is monotonic on the argument. If this product increases, the logarithm increases. And now this from very simple identities of the logarithm, we get that this is the sum of the radial coordinates of the nodes, which are the popularity coordinates, plus a logarithm that involves the similarity coordinates, and it can be shown that this is approximately the hyperbolic distance, which is given by this more complicated formula here. Okay. So by saying that new node connects to some existing nodes that minimize this product there, is equivalent to saying that a new node, when appears into the network, it tends to connect to the hyperbolically closest node to it. Okay. So here we see this this model in a growing version. So this we see the model in the picture of a growing network. So here is new node 20. It connects to some similar nodes. Most similar is node 8 and 7, and also to a hub, but not any random hub, because there is another hub here, a hub that is also similar to it. And it turns out this growing version of this model also reproduces many things that we see in the real network, many statistical characteristics of real network, degree distribution, degree-dependent clustering, distance distribution, betweenness characteristics, and so on. Not only in the internet, but also in other networks, trust networks, or social networks, biological networks, and many other networks. Okay. Now, so far we discussed about models and intuition. How can we put now these things, these ideas into practice, right? But before going there, let's have a bit of a small discussion about generative models, why they are useful, right? I mean, it's obvious. If you have a model that reflects reality well, then you can use this model to go the other direction through some, say, maximum likelihood estimation, or through some statistical inference that uses this model as a basis to do some inference. but the model has to be good, right? And the characteristics of a good model is that it has to be minimal or parsimonious. It means with minimum assumptions, it can reproduce as many things as possible. It has to be realistic. The thing that reproduces reflect reality. It doesn't reproduce other things. It has to be ideally mathematically tractable, so we can do some mathematics to understand more rigorously what's going on. It has to be reliable. This is a term that's actually quite important. It means that the model has to have some constraints, but it has to be maximally random in any other aspect. For instance, in random graphs, complete random graphs, two nodes connect with the same probability. Basically, there we fix the average degree of a node, and we randomly generate a network. Random graphs or Vertor-Rennes random graphs, they are unbiased, right? And they are reliable. But if you have, like, say, more constraints, like in random hyperbolic graphs, the way to go and prove this is by showing that your model maximizes Shannon-Gibbs entropy. And intuition of this, it means that when you create a graph, it does not generate anything else that you are not aware of, like substructures or some, I don't know, loops or whatever that you are not aware of. And maybe some other properties, but these are the properties we start with, and random hyperbolic graphs satisfy these characteristics. And in fact, the connection probability, the step function that we've seen earlier, in general, this may not be an exact step function, but maybe a smooth step function like a reverse sigmoid. And it can be shown that only this function leads to unbiased random. So this is the only function that leads to maximally random graphs. There are no other possibilities of this function. Okay, so once we have a good model, then if we given a real network with just the graph, we can go and start inferring the coordinates of the nodes in this network. And the basic approach that this is done is through a maximum likelihood estimation, which is given by, we first set up a likelihood as shown up there. So alpha ij is 1 if there is a connection in the real network between nodes alpha I and j, and otherwise is 0. Right, and P xij, P is the connection probability in the model. It's just like a reverse sigmoid. And xij is a hyperbolic distance between nodes I and j, which is a function of the coordinates of the nodes, the radial and angular coordinates. So imagine if you have this topology back then was 30,000 nodes, 30,000 nodes. We had to infer 30,000 radial coordinates and 30,000 angular coordinates by maximizing that thing there, which is, of course, something not at all trivial. This cannot be done analytically, cannot be done with standard machine learning approaches like Markov chain Monte Carlo or simulated annealing. It won't return anything of good quality here, maybe something not even approximately good to the quality that you can get if you think a bit outside of the box or a bit with different algorithms, because the likelihood there is abundant with deep local maxima, right? So, but back then here we devised a very simple heuristic, well, not simple, but it was efficient heuristic at least, that could perform this embedding. We embed this internally, the first hyperbolic graph of a network to what we believe is its underlying space. And what we got was something very, of course, according to our expectations and also even beyond. We could see that the nodes that belong to actual real communities, for instance, autonomous systems belonging in the same country, tend to cluster in narrow regions of the similarity space as expected. And also routing here is also very efficient, not as efficient as in the model, of course, because the real network, but in this mapping could reach like 97 success probability greedy routing following almost shortest paths in the network. So once we have a mapping like this, we can facilitate different things like navigation of greedy routing, prediction of missing links. So for instance, if two nodes here are close, but we do not see a link, there is a good chance that a link is missing between these two nodes, prediction of future links, community detection, and many other things. And actually recent work have shown that if you increase the dimension a bit more, by a bit more, I'm saying maybe you can go to 3 dimensions or 4, you can improve things. Things are already improved, so there is no too much space for improvement, but they improve, which implies that these 2 dimensions we use here, even if the space is hyperbolic, may be a bit more, but not what you would expect in a Euclidean space that would have 1,000 dimensions. There are no things like this here. So hyperbolic embeddings facilitate low dimensional embeddings. And the reason for this is exactly this. Yes.
Just understand the part of improving. So improving in terms of what?
In terms of grid routing, you improve by some percent. Or also the number one kind of improvement in the intuition is about the placement maybe of communities. So sometimes here you may see communities that overlap, that if you have an extra dimension to push them somewhere else, they wouldn't overlap and they would make more sense. This is a thing. And for instance, here you see Greece in this space close to Australia. Okay, I mean, this is not geographic space, but this may be an error of the embedding still. So it does improve, and there are inference methods very recent, actually 2023, that are based on these models that facilitate inference. They try to find the optimal dimension to embed the network, and they say, okay, it's low dimension, again, the embedding, but it's not 2, maybe something 3 to 7, something like that. But for more practical purposes and from analytics, the 2-dimensional embedding is also is already quite good. Maybe not the optimal, but already quite good. The bottom line is that you don't have to go to like 1,000 dimensions or something like that. Okay, and this has been extended in many other domains where the basic idea. So I will be going faster now because I think there's not too much time. So it has been extended, this idea, to bipartite networks, which are like networks where you have 2 sets of nodes, like customers and products that they buy, and they have links between them. To multiplex networks, so nodes in real networks can belong to multiple layers or networks simultaneously. For instance, we can belong in many social networks, or in the internet, we have autonomous systems that are both in IP version 4 enabled internet and IP version 6. They support both. So in the brain, we have structural networks and we have functional networks running on top of them. And what we found here is that in many different multiplex networks, the coordinates of the nodes are correlated. There are strong correlations between the coordinates of the nodes, and we can do different kinds of applications I'll discuss briefly. This geometry has implications on the robustness of networks, how easy we have shown, for instance, that they are robust to targeted attacks. If we start removing high-degree nodes, they can be used to efficiently dismantle a network to find the set of the minimum set of nodes that you need to remove to break a network into components, into the smallest number of steps. And have been expanded also in temporal networks. Yeah, so these are works that are participating. I'm not mentioning a lot of other works that other groups have produced. So these are not the only works. There are many other works about different aspects of these ideas, but this is still an emerging area, right? There are many problems. So here is, for instance, a bending of the IP version 4 internet and IP version 6 from this paper here. And the idea is that the coordinate of a node, say here, is correlated with the coordinate the node has in this layer here. So we can facilitate stuff like translayer link prediction. If we know the distances of nodes in one network, we can predict whether nodes would be connected or not in the other network, which is this like step function curve that you see there. We can do mutual grid routing. So if we have multiple layers, we can use them to get unstuck from local minima. So if I start from this red node there and I want to go to the green node and I have 2 layers, if I get stuck there, I can switch layer and continue from the top layer to reach the destination. And the interesting part here, which is also intuitive in retrospect, is that this process is optimized if the layers are correlated, but not maximally correlated. Because if they are maximally correlated, say they are identical, you don't get any benefit from these multiplexities, like navigating a single layer. If they are uncorrelated, it means that if a node gets stuck there, if it switches to the other layer cannot lead him to the destination because they don't have any relation between them. So there is a sweet spot that it has to be correlated, but not maximally correlated, the real layers. Then it has applications in robustness. So this is a picture here. I start this picture. Okay, I start removing high-degree nodes, and because there are correlations in this picture, in these networks, in this picture here, the dismantling happens slowly, slower than expected. And we see here we have some kind of not discontinuous transition. If layers say we're not correlated, which is this picture here, after a point where we remove a number of nodes, this thing will disappear after that point there. Once this line reaches that point there, it will disappear. And this is a case where this thing do not have correlations between them. So this is applications now to temporal networks like human proximity networks. So here are networks where there is a group in France that was collecting data, still collecting a sociopatterns corroboration about people moving in closed spaces like in schools, in hospitals, in workplaces. So they gave RFID tags to people, and if two people were meeting each other, there was a link in the data that they were collecting, and they were creating like these many high quality temporal networks of human interaction. And the motivation of collecting these networks is to study infectious diseases, respiratory diseases, or any other diseases. And back in 2017, we start studying these networks, and we saw that the kind of state of the art, let's say, model back then, it was a model of mobile agents that were performing random walks, basically, in a closed Euclidean space. And whenever they were within some range, they were stopping to interact with some time and then continue their walks. And then this simple model turned out to reproduce many temporal now properties that one is interested usually in these networks, like the distribution of contact durations, how long two nodes stay in contact, or how long it takes once nodes stop communicating until they start communicating again, so on. And we went there and we added an additional component, because random walks, if you think about it, is unrealistic, right? It's trivially unrealistic. I mean, if we are somewhere, we're not kind of, say, zombies, we're not performing random walks. We meet with people, again, based on some kind of attributes. So we added a similarity component in these walks that they were doing. So it was kind of semi-randoms, like Langevin dynamics. It was a directed random walk towards similar people. And what we see in this picture here with these particles, we're getting some graphs there that they have characteristics, again, like the graphs I described earlier. So we devised basically models also of temporal random hyperbolic graphs. So we sample graphs according to hyperbolic model, and then we go and do analysis to see what kind of temporal now network properties are reproduced, and we capture many temporal properties as well. And we can do mathematics here to prove the tail of the properties and so on. So this, and now this is many open problems now in this domain, this temporal domain. Okay. And now finally, I will finish about ongoing work. So in the ongoing work, what we say about until now, what we know is about basically, okay, we have a temporal model, but what we know is about static embedings. Like this picture here is a static embedding, right? But what if we could predict how these nodes will move in the future? Suppose you have a play button, you press the play button, this thing is moving, it may also be growing or shrinking, and you can press pause whenever you like. And then based on the positions of the nodes, you could say then whether they would be connected or not connected, right? So there's no theory that can do this thing right now, right? At all, no theory at all, not clue. Like say gravitational dynamics or molecular dynamics is networks, there is no such theory. And in fact, there was this is famous DARPA's 23 mathematical challenges from 2007. So they came out with 23 mathematical problems for the 21st century, and they had some funding announcement, but now this became popular, these challenges, because these challenges like problems like settling the Riemann hypothesis, mathematics of the brain, and then you see number 2, the dynamics of networks. So they put this problem next to problems like Occam's razor in many dimensions, settling the Riemann hypothesis, mathematics of the brain, and so on. And back then they were saying, develop the high dimensional mathematics needed to accurately model and predict behavior in large-scale distributed networks that evolve over time, occurring communication, biology, and so on. The good thing is now we know that we don't need high-dimensional mathematics, so we solve this problem by hyperbolic space, but we still do not know how to solve this problem, right? That's what was a mathematical challenge, I guess, right? But now we have some recent results, actually in collaboration with Vangelis that is here, that we say, okay, let's take many networks, map them into hyperbolic spaces, like for a long duration. It was a very hard task to get the data here, to find data here and perform this embedding, but we mapped data for a long durations. For instance, here, considering US air transportation networks, two airports are connected if there is a direct flight between them in the US. And we have data from 1988 to date. So we took this data. Fortunately, this network was not very big, it was about 400 nodes. So we could easily map into hyperbolic space, say 10,000 snapshots. And then we visualize now how nodes are moving in the snapshots. And here I will show some examples of LAX is the blue dot there, and LaGuardia Airport, which is the red node there, how these things are moving over time, right? Now, this is real time. Showing. Well, oh, this is, I think, the paper, I think it's not playing. Okay. Well, okay, it's not playing, but I guess it's okay. 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 Now we can visualize this, how they are moving over time. Okay, and the picture we get, first we get something that we cannot see in the subsequent slide, but we see some kind of synchronization. The first thing we see between the popularity coordinates of the two nodes. So when the popularity coordinate, which is that axis there, goes up of the one node, the popularity coordinate of the other node goes up. Even though these nodes are far in the space, and this we cannot still cannot explain. But in all trajectories we have seen from all real networks, many thousand trajectories, the picture we see is this picture here, right? So on the left, we see, say, the popularity trajectory on the Charlotte Douglas International Airport is the US Air Transportation Network. And we see something that has some trend. And even if there are 10,000 days, it's something that looks pretty predictable. It's not doing some random motion or some random walks or whatever. And if we compute the velocity, which is the difference of the consecutive increment or consecutive points in the trajectory, we get something that has negative autocorrelations or negative correlation. It means that whenever there is a positive increment on the velocity, then in the subsequent time step, the probability, there is a high probability for the increment to be negative, right? And we can draw the autocorrelation function, which quantifies this thing. And we found that in all real networks, they have negative autocorrelations. And specifically, the autocorrelations can be well described by that formula there, which is the formula from fractional Brownian motion process. H there is called the Hurst exponent. And in all real networks we have studied, this H is usually below 0.5. And in the vast majority, or at least in many cases, it's much below, well below 0.5, which means that the trajectory is basically are anti-persistent or mean reverting, and they have short-term autocorrelations. Anti-persistent, it means that if it goes up, in the subsequent step, it has a high chance of going down. And then we draw plots something like these that they are called variance time blocks, where not going to get into details. The idea is that you cut the velocity process into blocks, you sum up the increments in each block, and you find the variance of these summations. And in a self-similar process, the variance according to the block size M is the block size, should behave according to this formula here. Sigma square is the variance of the original process, and H is the estimation that we make of the Hurst exponent. And we found that in all trajectories, we can match the variance kind of using this idea here. And we find again the same with similarity trajectories. So this would be appear in PRL. This study here, soon was also selected as editor suggestion, was very good. First time this happens to me. So I guess the editor really liked the paper. But the results there were not only this, we explain also in the paper why we see what we see. And we also develop a model that can construct synthetic trajectories, a fractional Brownian motion model based on the Riemann-Liouville fractional Brownian motion model. And we can reconstruct synthetic trajectories that match real trajectories. So we understood the process that the trajectories are following, the stochastic process. And we also demonstrate some predictions. Once we have this model, how we can do simple predictions of trajectories. But of course, this problem It's not solved, it's only the beginning because we can do simple predictions like this, but we cannot predict if trajectories will change trends or if trajectories will not basically following what we were seeing in the past. But here we study trajectories independently, and the future work consists of studying trajectories dependently because we observe also some synchronization phenomena between trajectories. And of course, we expect trajectories of not being independent, that one can influence the other. And yeah, an idea here is whether we can fit some neural network with a bunch of trajectories and see whether it can predict if trajectories, if trajectories change trends, whether the neural network can predict that they will change trends. But given that we are doing everything correctly, we didn't manage to do this with any neural network. And the results actually, even in these simple cases, which is model-based, we never got better results than this. But maybe we're not doing things correctly, I don't know. It was very fast. Okay, but yeah, but we are working on more like principal models of how we can do these things and how we can do predictions. And this is a final slide. This is collaborators. So it's not only me, it was maybe yeah, maybe I should have mentioned from the beginning. So it's Dima Kriugov from Northeastern University, Marian Bocunia, Mariangela Senaro, University of Barcelona, it's Maxim Gitsak from TU Delft, Philip Poradicis from Indiana University, Kostia from Caltech, Goya now Swiss Industry, Said at Max Planck, Harrison at Santa Fe Institute. And this is local team, it's Kostas Somas, was my first postdoc in Cyprus, now University of in Cyprus, and now with the University of Cyprus, a researcher. Marco, my PhD student, graduated switched to industry, created a startup. And Kostas and Sophocles were my latest postdocs that now Kostas is at the European University, assistant professor. Sophocles continues postdoc in a center of excellence at Athens. It was also Vangelis also last year, but I couldn't find any picture of Vangelis, but you have him there. I couldn't find any picture, but he's there. So you can make one now. Okay, so thank you very much. So more or less on time.
And I mean, I mean, these embeddings that you do in this kind of world spaces are very low dimensionality, and in machine learning, you know, we compute embeddings over graphs using models that are very, very high dimensionality, and they actually work like extremely well. You can reproduce any property of the network you want. Of course, they come from black boxes, right? So I think I know the answer, but I would like you to kind of articulate the pros and cons of the two approaches. The approach that you propose, which is much lower dimensionality, versus the machine learning approach.
Oh, there are actually there are many. Well, there are many cons basically. If you go high dimensionality, first you have to search for the dimension, right? What is the right dimension? Second, it can influence how accurately you can do the maximization process. So you have to, if you are in high dimension, maybe the problem, how certain you are finding, say, the maximum in the likelihood function. And that's, yeah, the main problem is you have too many parameters. Here we want to understand what's going on and how you can do, say, mathematics, how you can analyze things with 1,000 parameters. And the other main thing is I don't know how generalizable this is, right? So you have a bending for maybe a neural network bends a specific or a specific procedure to embed a specific network, say, in 1,000 dimensions, and then you get some other network. How do you know the dimension of the other network? So I'm not sure about the generalizability of these approaches. So if you get a specific, I don't know, architecture, you embed a network, and then you take this architecture and bend it to another network. right, that are say from different domains. I don't know the generalizability, and I don't know how you can do mathematical analysis to understand what you are doing. But yeah, I mean, maybe it's more automated. Yeah, but I think now also in machine learning, they're turning every year in machine learning in these top conferences, NIPS, ICLR, there is something about hyperbolic. There are hyperbolic attention networks, hyperbolic neural networks, hyperbolic graph convolution. There are many hyperbolic things now. They understood that the natural embedding or the natural space is hierarchical, is not Euclidean. So since 2017. Yes.
How do you see the future of network geometry in tackling complex nonlinear multi-source, multi-layer problems like climate crisis and cancer? Yes, what's the future of network geometry? How do you see in evolving in applications in tackling nonlinear complex multi-source, multi-layer problems like climate crisis, cancer?
Well, I mean, there are many applications depending on the domain. There are applications now in brain networks that use hyperbolic embeddings. There are applications, so there is an emerging also area, it's called network medicine, network science, so how diseases are connected to each other. And the idea is if you can find links between diseases that you didn't know before, and then you go and you have to map them into some space to see, look, it's like a missing link prediction problem that you have in hyperbolic space. So you have applications there, you can represent if you embed disease networks, protein interaction networks about missing interactions. Yeah, and also now there is also some, especially in protein interaction networks, it has been shown recently relatively that maybe it's not similarity what matters there, but complementarity. Because they tried to do these embeddings there, but there was no this triangle inequality. They had to rethink a bit of the problem. And there is this idea also that there are some complementarity principles taking place. Yes, say you are performing a functionality and then some other functionality that complements yours and you cooperate to perform a task. So this is called complementarity. So what I was talking until now is similarity only, but there is networks that are maybe collaboration networks, financial networks, but also in biological networks, especially protein interactions that may be formed by complementarity. So this is also, but the idea is this link prediction problem. You represent things into the space and you can see things that maybe you cannot see from the graph. And then you can also perform this navigation to see how from one node you can go to the other that you may not be able to see from the graph.
Any other questions? Thank you, Professor Papadopoulos, for the presentation. We can continue our conversation outside with drinks and snacks. Thank you.
Thank you. Thanks. Οπότε βγάλω το απλά το φαντάσου. Okay.
Έχετε κάποια συνάντηση τώρα ή... Έχει snacks έξω να... Και νερό εδώ, αν διψάτε. Τέλεια.
Thank you.